So I'll be presenting some of the results from my PhD research. My PhD research was about finding optimal call allocation policies in small call centers. So let's start by defining a call center. The term call center is commonly used to describe a telephone-based human service operation. A call center provides teleservices to its customers, namely services in which the customers and service agents are remote from each other. A call center service provider is a company that has multiple clients, and under the contracts that they have with their clients, they have to manage their client's customer care department while meeting certain monthly targets, such as serving at least 90% of the calls within 20 seconds and keeping abandonments under 3%. You can think of a call center service provider as a call center expert, and other companies outsource their customer care department to these service providers. But the companies still want to make sure that their customers are served right. Hence, in the contracts that they have with these service providers, they put these constraints where they're generally monthly constraints where, for example, they have to keep abandonments under a certain threshold number. My PhD started as a contract with one such service provider, and they approached us with the problem that they were struggling to meet the targets set by the clients despite high non-occupancy rates among its agents. So the agents that they had were not occupied on the call for a significant proportion of the time, but still they were struggling to meet the targets set by the client. So what all can be done in such a scenario? We could try finding a better prediction model to increase the accuracy of the predicted workload. So in a call center, there are a lot of uncertainties involved. They don't have an appointment system. They don't know when the customers are going to call, what they will be asking, and how much time it will take to serve a customer. So they use past data and a prediction model to see what an upcoming day is going to look like. And a better prediction model means you're better prepared for it. You could find a better model that fits the service and the abandonment time data. Again, using the past data, you can be better prepared on how much time it will take to serve a customer or how much patience level your customers have. You can find a better estimate of the number of staff required at each level. So even if you have a better prediction model, there's still a step where you need to decide how much staff you will need for every shift. This includes scenarios like you have to meet government regulations and other human factors, such as an agent might call in sick, the agents might not be as efficient, there are other unpredictable factors, so you still have to find an estimate of the number of staff required. And the last one, which I focused on, is finding a better call allocation strategy. A call allocation strategy refers to the rules that a call center uses to assign an incoming call to an agent. So in a call center, there are different ways of assigning an incoming call to an agent. And I will talk about some scenarios where you can find an optimal way of doing this. Let's first take a look at what happens when a customer calls a call center. When a customer calls a call center, they're first connected to an interactive voice response system. This is the automated voice which you hear when you dial a call center. It tells you to dial number depending on the type of query you have. In certain scenarios, the queries get resolved by the IVR itself, but in other cases, the customers are looking for some human assistance. If the customer is looking for an agent, the IVR will look for a suitable agent for that customer. So, depending on what the customer dialed according to their query, the IVR will try to find an agent who can take that type of query. So, for example, if a customer has a technical query, an agent who is only skilled at solving sales query cannot take that call. So the IVR will look for a suitable agent for the customer depending on the number they dialed. If such an agent is available, the customer gets assigned to that agent and eventually gets served. If no such agent is available, the customer gets added to the queue where they wait either until they do get assigned, or they can choose to abandon the queue depending on their patience level and worth of that service for them. So in a call center, different agents have different skills. Some agents are skilled at solving just one type of query, and some agents are skilled at solving more than one type of query. So whenever there is a call coming in, there's generally more than one way of assigning that call to an agent. And depending on how you assign it, you can increase the efficiency and performance of the call center. Let's take a look at an example to see how this works. Consider this call center. In this call center, there are two types of queries coming in, either a sales query or a technical query. And there are two types of agents available. Type 1 agents are, say, newly hired agents, and they can only take sales queries. And type 2 agents are more skilled agents, and they can take both sales and technical queries. The green agents are available agents, and the red agents are the agents who are already busy on the call. Now, say some type 1 agents are available and some type 2 agents are available, and a sales query is coming in. In such a scenario, the optimal action would be to assign the sales query to a type 1 agent, since they are dedicated sales agents. And similarly, if a technical query is coming in and a type 2 agent is available, the optimal action would be to assign the technical caller to a type 2 agent, since they're the only type of agents that can take that query. But what happens when sales query is coming in and all type 1 agents are busy, but some type 2 agents are available? In this case, should you assign the incoming sales query to this only available type 2 agent? In that case, you will block the type 2 agent from taking a technical query in the near future. Or should you add the sales query caller to the queue, where there's a risk that they might get impatient while waiting and abandon the queue? The optimal action in such a scenario depends on multiple factors. For example, what are the arrival rates of a sales query caller and a technical query caller? It could be that on any given day, on average, you only get 1 or 2 technical calls. In that case, you might not want to reserve the type 2 agent for that one technical call that might or might not come. It also depends on the service rate, how much time it takes to serve a call, the patience level, and also the worth of the caller for the company. So it could be that for the company, a sales caller is more important than a technical query caller. Maybe because the sales caller is a potential new customer, whereas a technical caller might be already an existing customer. So if a sales caller abandons, it's more costly than if a technical caller abandons. Our job is to include all these important factors and then come up with a way to find the optimal action in scenarios like this. The call center that I worked with had a structure similar to this. So instead of 2 levels, they had 4 levels. There are 4 levels among the calls, and there are 4 levels in the agents as well. The levels are such that level 1 calls are the simplest calls to handle, and level 4 calls are the most complex calls to handle. And among agents as well, as the levels increase, the agents get more skilled. So level 1 agents can only take level 1 calls, level 2 agents can take 1 and 2, and similarly, level 4 agents can take any of the calls. Again, there are calls arriving, they get assigned to the IVR system, they go to the IVR system, where the IVR segregates them among the 4 levels, depending on the number they dial. And then if an agent is available, the calls get assigned to the agents, otherwise they get added to the queue, where they might choose to abandon the queue, or they eventually get assigned and served, and then they depart the system. So this is the background of the problem and the motivation. Anyone has any doubts so far? Okay. So moving on, we decided to model the system as a continuous time Markov chain. We assume that the calls at each level are arriving according to a Poisson process, and the service time and abandonment time are exponentially distributed. Our objective is to determine a policy that takes the optimal action at each transition so that the expected cost of abandonments is minimized over a finite time horizon. So let me just break this sentence. The objective is to find the policy that takes optimal action at each transition. By transition, I mean arrival, service, or abandonment. These are the three possible transitions that can happen in a call center at each level. And we want to minimize the expected cost of abandonments. So this is one performance measure. I will focus on this performance measure. There could be other measures as well. We want to minimize the expected cost of abandonments over a finite time horizon. So we're looking at a finite time horizon because in a call center, the state changes throughout the day. There are different shifts, the number of agents available at different shifts changes, and there could be things like they are getting more calls in the morning and in the evening, but not that many calls in the afternoon. So that's why we just want to work with a finite time horizon, and we'll be minimizing the expected cost of amendments. We first consider a downsized system. So we consider a system with two levels of agents and callers. Level 1 agents can serve only level 1 calls, whereas level 2 agents can serve both level 1 and level 2 calls. So similar to the example I showed above, I will go back to the 4 levels case at the end of the presentation, but for now we're just working with 2 levels. In a call center system, there are 2 types of state transitions that require decision-making: call arrivals and service completions. So the transition includes arrival completions and abandonments, but in case of abandonments, there is no decision-making required. A caller abandoned the queue, you can't do anything about it, you don't have to take any decision. But whenever there is a call arrival and a service completion, you do need to make a decision. At a call arrival, we must decide which available and skilled agent, if any, should serve the call, or whether to place the call in the queue. At a service completion, we must decide which waiting call, if any, should be assigned to the free agent, or whether to keep the agent reserved for a future arrival. So these are the decisions we need to make at certain transitions and state space. Now let's talk about the state space and the state of the Markov chain. Let SG be the state space, and this vector represents the state of the Markov chain. We have 5 state variables, where A1 be the number of level 1 calls being served by level 1 agents, A2 be the number of level 1 calls being served by level 2 agents, AQ be the number of level 1 calls waiting in the queue, B2 be the number of level 2 calls being served by level 2 agents, and BQ be the number of level 2 calls waiting in the queue. So A represents level 1 calls, B represents level 2 calls, and the subscript represents like the state of that caller. So are they being served, and if they're in the queue. Just a little diagram to maybe helps you remember these variables. Level 1 agents are serving A1, and AQ are waiting in the queue. And level 2 agents are serving A2 plus B2 calls, and BQ are waiting in the queue. Let's first take a look at the discrete time model, because it's much easier to approach, and also there's first proper literature for the discrete time model, and then I'll go back to the continuous time case. In the discrete time model, what we're trying to do is minimize the expected cost of abandonments, but instead of saying for next 2 hours, we say for next, say, 200 events, where events refer to any transition that happens: arrival, service, or abandonment. So each event, we refer that to as a time step, and we're trying to minimize the cost over certain number of time steps. We now define the value function for this model. So let VMS denote the minimum expected cost of abandonments between time steps M and capital M, where given that the system is in state S at time step M. And we set the boundary condition at capital M equals to 0. So VMS here represents the minimum expected cost of abandonments between small m and capital M. And we know the state at small m. And because we are just talking about the cost of amendments between these time steps, at the boundary, we put VMS equals to 0 because we're not counting any amendments that happens after capital M. The final goal is to find V0S. We want to minimize it over the entire timeline. But why is it difficult to find V0S? Because at every time step, there are different possible transitions that can happen. And different transitions lead to different, like every transition has some actions that you can take. So even if you have to take two actions, you have to decide between two actions at every time step, that gives you 2 to the power m possible policies. And finding the best policy among those many policies is obviously a difficult problem. Hence, we're going to use Bellman's equation. Bellman's key insight was that instead of solving the full optimization problem from 0 to m, we can simplify it by optimizing one step at a time from m to m plus 1, assuming we have access to the value function at time m plus 1. So we already know the minimum cost of abandonments from time m plus 1 to capital M, and we just want to minimize over at one additional step from m to m plus 1. We already know the state at small m, so we know all the possible actions. We can calculate the cost in all the possible actions between time m to m plus 1, and then we add it to the cost at m plus 1 and find the action that leads to the minimum sum of this cost and this already optimized cost. Formalizing this, using the value function, the optimal expected cost at time m is given recursively by this equation with the following boundary condition. So again, we want to calculate VMS, which can be given by the minimum value of the cost at time step m plus the expected cost from time m plus 1 onwards. We're taking an expectation because we don't know what this state is going to be. It depends on the state and action. So we take expectation over all the possible states that can be there at m plus 1 and find the action that leads to the minimum value of VMS. Because we know the boundary condition, we can perform a recursion backwards from m minus 1 to 0. Storing the action that leads to the minimum value provides a pathway to determine an optimal policy. This recursive solution method is known as dynamic programming. So we're going to use this method on our call center system to find the optimal allocation policy. One would normally expect the optimal policy to assign a lower level call to a higher level agent whenever a higher level agent is available. This is the work conserving policy, and it would be our first guess as the optimal policy. In cases where the difference in the abandonment rates and the cost of abandonment between the two levels is small, this holds. So this is the optimal policy for a lot of cases. However, this is not always the case. Let's take a look at a numerical example when that's not the case. We use Bellman's equation to determine the optimal policy for the set of parameters given in the table below, with total capacity L equals to 20 and horizon M equals to 100. So we're finding the policy for next 100 events, and the capacity of our call center is 20. So at any given point in time, there can be maximum 20 customers in the call center. If a customer comes in when there are already 20 customers there, they get blocked. This is the set of parameters that I'm going to use. There are two levels, level 1 and level 2. They each have their arrival rate, lambda I. So here I'm keeping them equal. The arrival rate is 1 per minute for level 1 and 1 call per minute for level 2. The service rate by the same level agents. So if level 1 customer gets served by level 1 agent, the service rate is 1 by 4. Similarly, 1 by 4 for level 2. Service rate by higher level agents is also 1 by 4. So I'm keeping everything equal just for the simplicity, but you can change these parameters, have different parameter values at different levels. A rate of 1 by 4 implies it takes on average 4 minutes to serve a customer. Abandonment rate theta I is 1 per minute for level 1 and 2 per minute for level 2. So the customers at level 2 are twice as impatient as customers at level 1. Number of agents Ki, 5 agents available at each level. And the abandonment cost gamma I is 1 unit if level 1 abandons and 2 units if level 2 abandons. So you can think of this set of parameters as something for an airline call center, where level 1 customers are the economy class customers and level 2 customers are business class customers. They are paying more, so they expect better service, hence they're less patient. And if they abandon, they cost twice as much as if level 1 customers abandon to the airline. So again, just a small example to show how this exactly works. We consider the state 51120. That means there are 5 level 1 agents serving 5 level 1 calls. So all level 1 agents are busy. There's one customer waiting in the queue. Out of 5 level 2 agents, 3 are busy, 1 with level 1, 2 with level 2, and there are no customers at level 2 that are waiting. What happens when another level 1 call arrives? So there's this 1 becomes 2, and now we need to decide, should we assign that one of these 2 level 2 agents, or should we add that one to the queue as well? And what happens when a level 2 agent completes a service? If one of these agents got free, should we now assign this waiting call to that agent, or should we not? Should we just reserve that one as well? So in case of an arrival, you have 2 possible actions, assign and queue. And in case of a service, you have 2 possible actions, assign and do not assign. In total, this gives you 4 possible set of actions. Under each set of actions, your VMS will evolve in a certain way. So if you have assign and assign, so assign when there is an arrival, assign when there is a service completion, you will have a certain value of your VMS. Similarly, in the second set of actions, queue and assign, your VMS will evolve in a certain way. Similarly for action 3, which is assign and do not assign, and action 4, which is queue and do not assign. For given values of VM plus 1, s, we choose the set of actions that minimizes VMS. So out of 4 possible set of actions, we will choose the one which leads to the minimum value of the value function. And similarly, by proceeding backwards from time step m to 0 and considering all states, we can determine the optimal action for each state and time step. Let's take a look at the optimal policy that we will get using this method for the set of parameters I showed you before. We're going to look at the optimal policy at the time origin, so m equals to 0. When all agents are busy and a level 2 agent completes a service, the optimal policy says that if both level 1 and level 2 calls are waiting in the queue, it is optimal to assign a level 2 call to the agent. So if both of them are waiting, we give priority to level 2 call. If only level 1 calls are waiting in the queue, the optimal action is to keep the agent idle. So if one agent just got free, we are not going to assign this level 1 call to that agent. We're going to keep them reserved for a future level 2 arrival. What happens when not all level 2 agents are busy and level 1 callers are waiting in the queue? So we already know that if both of them are waiting in the queue, the priority is given to level 2. But what happens if just level 1 callers are waiting in the queue and more level 2 agents are available? In that case, the optimal policy actually is quite complicated given by the table here. I'm not going to go in the details of the policy, and the idea is that the optimal action depends on how many agents are available at level 2 and how many customers are waiting in the queue at level 1. So if more agents are available, the optimal action would be to assign the call that's waiting to the agent, because we have more than enough level 2 agents and we can afford to assign a level 1 call to a level 2 agent in that case. If there are few level 2 agents available, for example, 1, and there are few callers waiting in the queue, the optimal action is to not assign a level 1 call to a level 2 agent in case of an arrival or a service. Similarly, for different set of these variables, you get different set of actions. If there are more callers waiting in the queue, the policy is more flexible about assigning level 1 to a level 2 agent. So say if there are 11 to 15 callers waiting in the queue, there are way too many waiting, you assign a level 1 call to a level 2 agent when there is an arrival or a service. So all in all, the observations are that the optimal policy is a bi-threshold policy that depends on both the number of agents available at higher levels and the number of callers in the queue at lower levels. The general optimal policy is time dependent and is also sensitive to the parameter values. So we looked at the policy at time step m equals to 0, But if you look at the policy at some other time step, it could be different. So it is different. Generally, it stays the same for, say, first 50 time steps, but eventually, as you go closer to the time horizon, the policy starts to change. So it's time dependent, and as we saw, it's quite complicated. So obviously, if we change the parameter values, the policy changes as well. The optimal policy becomes more flexible as we go near the time horizon. And one of the possible factors is our choice of the value function at the boundary. So remember that at the boundary, we put the value function equals to 0, and that obviously affects the policy, the optimal policy near the time horizon. Hence, we consider just the optimal policy at m equals to 0. So yeah, this was one of the models that I used to find the optimal policy. Just want to ask again if there are any doubts so far before I move to the last third half of the presentation. Okay. If not, then moving on. What about performing this analysis in continuous time with a finite horizon? Ideally, we would like to perform this analysis in continuous time over a finite horizon without assuming stationarity. Of course, continuous time is a more realistic setting for a call center. However, when I try to extend a similar analysis like Bellman's equation to continuous time, I face two major challenges. The first one is that within a finite continuous time interval, the number of events that can occur is uncertain. So we do not know how many events will happen in next 2 hours. So that's uncertain, and that's one of the challenges, because in Bellman's equation, we need the value of capital M to perform that analysis. And the second problem is that deriving an optimal policy would require evaluating the expected number of abandonments across all states and every instant in time, which is, of course, infeasible. So remember how we calculating VMS based on VM plus 1S, but if the time is continuous, you would need that as a continuous function of time. And calculating that is, of course, infeasible. Hence, we perform this analysis of identifying the optimal policy using 3 different approximations. The first one is the discrete time jump chain analysis. That's what we saw. The next is infinite horizon continuous time models with discounting. So you can perform an analysis in continuous time, but with infinite horizon, because then you don't have a time factor. So it simplifies the equations, and you can use iteration methods to find the value function in infinite horizon continuous time case. And the last one is a heuristic method that I kind of developed using by extending the approximate value iteration. So a finite horizon continuous time iterative method extending the approximate value iteration. Approximate value iteration is a method that's used in discrete time, but I try to extend it to continuous time. This method, it gives sensible policies, but not as optimal as the two above. It's one of my future research goals to find a way of finding the optimal policy in finite horizon continuous time case. These 3 methods are used on the same set of parameters, and the 3 methods, they agree with each other. All 3 methods give you a bi-threshold policies. There are small differences, but more or less it's the same policy. So next, we developed a method using Markov chains for step analysis and Laplace transform that allows us to calculate performance measures exactly for a given policy in continuous time with a finite horizon. However, this method does not identify the optimal policy. So identifying the optimal policy is the first part of my research, and the next half is to evaluate those optimal policies. That I can do in continuous time finite horizon case, but this one does not allow you to find the optimal policy. Therefore, we first use the approximation methods described earlier to indicate the class of optimal policies, and then apply this exact method to evaluate the performance of policies within this class. Now, we'll briefly talk about this method and how it allows us to evaluate these optimal policies. So let's first look at the class of optimal policies that I will be focusing on. Reservation policies are threshold-based policies that depend only on the number of available agents A lower level call is assigned to a higher level agent whenever the number of available higher level agents exceed a specified threshold. So I'm going to focus on reservation policies, and this class of policy is a single threshold policy. It only depends on the number of agents available. I'm not doing this analysis in bi-threshold policies because first, the reservation policies require fewer state space variables and also a smaller action space, making it feasible to extend to 4 levels, which was our original goal to do this analysis in 4 levels. Second, when we performed simulations on the reservation policies and the bi-threshold policies, we saw that they perform almost as well as the optimal policies derived using the approximation methods above. So reservation policies perform almost as well as the optimal policies. They're also more robust, easier to understand, and simpler for call centers to implement and adapt. So I'm going to perform analysis on these reservation policies that are single threshold policies, and the goal is to find the optimal threshold and evaluate the policies for that optimal threshold. I briefly discuss here the steps that I use to evaluate the performance measures. To calculate the performance measures for these policies. But I will not go into the details of it, but just a brief methodology on how I can calculate the transient performance measures for reservation policies. The first step is to assume that we know the state of the system at time 0. It's a reasonable assumption. We then perform the first step analysis to find the relevant quantities conditional on the first departure time. So first step analysis is a common first step for analyzing Markov chains. And the relevant quantities here refer to whatever performance measure you're looking for. So I calculated different performance measures. We were talking about cost of abandonments, and then we can also calculate the average waiting time, the number of services that happen, and most importantly, we can also find the waiting time distributions of the customers. This allows us to answer questions like, what is the probability that a customer who arrives in next 2 hours is going to get served within 20 seconds? So such kind of performance analysis that you can do using this method. The third step is to remove this conditioning by using exponential distribution waiting time, this conditioning on the first departure time, which would lead to convolution integrals. And then in order to deal with the convolution integrals, we take the Laplace transforms and solve the equations that are satisfied by these Laplace transforms. And then we invert the Laplace transforms using numerical methods to calculate the original quantity. I can use these 5 steps to calculate different performance measures. And I'm not going in the detail of maths because this is what the Laplace transform in the 4-level case looks like. It's scary, and I can talk about it more in detail if anyone's interested, but yeah, that's like one of the examples of the Laplace transform equations for 4 levels. Jumping on to an example for the 4-level case. So we are going to find the cost of abandonments for this set of parameters for different threshold policies. There are 4 levels, level 1 to 4. There are some arrival rates for these levels, service rates. Then you have the abandonment rates. You have the number of agents available. And then you have the cost of abandonments. The question is, how many agents should we reserve at each level to minimize the expected cost of abandonments during next 60 minutes or 60 time units? And this is the kind of output that we get using the method above. Here, each row represents a reservation policy. Theta 2 is the number of agents we reserve at level 2 to exclusively serve level 2 customers. Theta 3 is the number of agents we reserve at level 3 to exclusively serve level 3 customers. And similarly, theta 4. And C theta, 60 refers to the cost of abandonment for this particular reservation policies in the next 60 time units. So if you do not reserve any agents at any level, the cost of abandonments comes out to be 7.78. If you reserve 1 agent at level 4, the cost drops to 7.13. If you reserve 2 agents at level 4, the cost is 7.79. And similarly for all other reservation policies, if you reserve all the agents at all the levels, then the cost is 13.60. Now, using this table, we can find the optimal reservation policy, which is 001 in this case. I'm using enumeration here, but I've also used black box optimization to find the optimal policy, and it usually works, gives a good result. One of the future goals for this research is to find an optimization technique that is suitable for finding the reservation policies for this problem. So the main hurdle that I have while applying traditional optimization methods here is that I'm inverting the Laplace transforms numerically, and that makes it difficult to use the traditional optimization methods. So I'm using enumeration and black box optimization at the moment. And this is the cost of abandonments, but similarly, you can find other performance measures. For example, as I said, waiting time distributions of the customers, and you can do it for any initial state, for any time duration, and find the best reservation policies for the call center. Okay. Some of the future research goals. We would like to scale this method to handle other call center structures, bigger call centers, and more levels of agents and callers. I have applied this method on a different call center for a multilingual call center, which has a different structure, but it is still hierarchical. It would be nice to extend this method to call centers that do not have hierarchy among their agents. And bigger call centers also comes down to writing better code, more efficient code. And again, more level of agents and callers also, more efficient code would help with that. I would like to develop more accurate and computationally efficient method for solving finite horizon continuous time Markov decision processes. Is something I really want to pursue in the future. Use problem-specific optimization algorithms to calculate minimum staffing requirement. As I said before, anyone has any suggestions on what optimization methods I can use for this case, that would be great. Then we have extend the analysis to systems with other arrival and service distributions. So right now I'm using Poisson and exponential. It's nice to extend that, although I think this is going to be very difficult. And the last one is to combine our framework with arrival rate forecasting to produce real-time allocation recommendations. So something with machine learning where you can have like an online learning system in the call center where it learns in the real time. These are the references that I mentioned, and that's all. Thank you.